Well, good afternoon. We have a full room today, so really exciting. So my name is Francesca Dominici. I'm the director of the Data Science Initiative, and it's my really welcome you all. And it's really my pleasure to introduce Mauricio Tec, will be teaching the session this afternoon. So I am a big fan of Mauricio. Mauricio is a research associate that is joined between the lab of Milin Tambe, who is a professor of computer science here, and in my lab. So he's been splitting the time between the two groups, which means that he has at least 2 full-time jobs. His focus is on training agents with foundation models using method from reinforcement learning, diffusion generative model, and large language models. On the apply side, he's also very interested in autonomous agent system and social impact applications. He's working on a lot of stuff, but among the 3 focus that he has is leveraging large language models for reinforcement learning, particularly for improving explainability, generalization, and as engines for generative agent-based simulations. Second, he leveraging diffusion generative models as powerful engines for causal reasoning and planning. And third, developing new representation learning methods for decision-making task. Now, about his bio. So he has a PhD in statistics at UT Austin, focusing on reinforcement learning and computer vision applications. And he was also a member of the Learning Agent Research Group at the Computer Science department. He has a lot of passions. One passion that he has is in building robots. Another passion, he is really picky about making espresso coffee, which is a wonderful feature to have, especially when he's spending time in a lab with a lot of Italians. So we're very happy, Mauricio. The other really unique thing about Mauricio, you can go on his website, and he's one of the first that build a large language model on his CV. And so there's actually a chat box on his website where you can ask questions about him. So I'm going to stop here, and I'm going to turn it to you, my friend.
Thank you. This is always very kind. Okay, is the audio good up there? Okay. I'll do my best to speak loud, but just let me know if I'm speaking too loud or not. All right, so welcome everybody to the LLMs as Autonomous Agents tutorial. And I hope all of you did your pre-assignment. If you did not, don't worry, but here's the web address, here's the address as well. And if you wanna, this is a hands-on tutorial. And if you wanna follow along, it's good that you do the pre-assignment to make sure you have all the key API keys and everything. I'll remind you on time also when we're going to need them. But if you don't, or if you don't have your computer, don't worry. You can also follow along. And so I'm going to give you first the outline of today's tutorial. We're going to spend about 10-15 minutes in general, like just a really broad view of agents. Then the first part of the hands-on tutorial is going to be on an introduction to agentic frameworks. In a minute, I will say what we're going to cover. And in the second part, we're going to ground the agents on with fine-tuning and reinforcement learning. And this is a fully hands-on tutorial. So there will be very few slides. I'm already like 20% on my slides. And we're going to do modern Pythonic libraries. Well, the light's really in my face. So we're going to use small agents, which is pretty cool. It's something that only came out in December 2024. And from the libraries I know, it's like the most minimal. So it's like really perfect for getting started on the agentic world. And then we're going to get our hands dirty with PyTorch and transformers. And I want to say this is not a research survey. It's not the kind of tutorial where you're going to get an entire literature review. There's already pretty good materials out there. I really thought this tutorial for getting hands-on experience coding. And what do I mean by hands-on experience? Well, we want to understand the main design components of LLM agents, and part one is going to be probably the most fun because we're going to do a lot of examples, and we're going to make an archive paper explorer. We're going to do an automated data wrangler that can create plots, and we're going to do a GitHub repo explorer, which also helps you create a template for your project. And all of this, incredibly, is only going to be a few lines of code, which I find really amazing. And then part two is going to be scary. Then we're going to download a 1 billion model, and we're going to fine tune it. We want to do reinforcement learning, and for that part, of course, that could be an entire course, entire 1 semester course, and I've done my best to compress it. But there are going to be obviously some concepts in the machine learning part that I will be of course not cover in depth, but I think I hope give you a flavor of what's the of this important task. And this is meant to be fun. If it's not fun, you can leave. But I promise you I'll do my best to be fun. So about me, Francesca already did a very nice job on introducing me, but I just want to say to you, I always loved agents. I've done a lot of research, but agents has always been at my heart. And as you know already, I'm a research associate at the Department of Computer Science and Biostatistics. And I work on LLM agents, foundation models, and decision making. And I publish my work in top-tier computer science conferences, and I focus specifically on social impact and public health applications. And back in my PhD, I'm a PhD in statistics, but I was very focused on agents. I competed at the UT Austin. I competed at the RoboCup. So this is me actually in Bangkok in a robotic competition. So that was one of those were agents too. And when I convince you that those are not different agents than the ones we're going to code, right? And besides participating in the RoboCup, I participated in a competition called Text World. And this is what we're going to do in our tutorial number 2. It's been a while since I participated here, and LLMs have improved. So I just want to see if we can do better than that time. And then my background is in mathematics. I went to the University of Cambridge. I did my master's there, and before that, I did my bachelor's in Mexico City at ITAM, also in mathematics. So,
Mauricio, I'm not sure your mic is on.
Okay. It is on.
Now it is.
But
Where was it?
it is not directed. Let's see. Does this positioning help a little bit more?
Yes.
Okay. And maybe there was a volume here, but I forgot. Okay, I hope this is better, and I'll speak slowly or clearly. All right, so getting started. This is a $1 million question. What is an LLM agent, right? And let's start by saying agents in general are computer programs that can act autonomously. And then the key word is act, right? So this means that LLMs on their own, they're not agents. And so what I mean LLMs on their own is LLMs are language models. They're designed to predict what the next token, what the next word's going to be after a sentence. So that doesn't make them act. But that being said, their ability to predict language have led to clever techniques to control the flow of a program using LLMs. LLMs decide what to do based on their capability, and that's when we have an agent, when we're able to have a computer program that the LLM is dictating how it's going to behave, right? And it's a little abstract right now, but you can think of LLMs that can use tools and LLMs that can interact with some environment, and that's when we have an agent. So here's a question for you. Which one is a year of agents? Is it 1995 or is it 2025? Right? So here we have the latest news. OpenAI says we're on the verge of AI agents. NVIDIA CEO says 2025 is a year of agents. And then we see these really old papers called Architecture for Agents that Track Other Agents in Multi-Agent Worlds, right? 1996, 1995, Intelligent Agents. So which one is a year of agents? Then, well, what happened today is we saw an explosion of agentic frameworks fueled by the LLMs. And so I've heard some people, Andrew Ng is very famous, and I heard him say this is a prototyping revolution. It was never this easy to, as we'll see in our examples, to make such complicated applications that put together different components in only a few lines of code. And it's really impossible to keep track of all the frameworks. I have here for you a link to all the different frameworks for different purposes, and we're going to use one here. But the key point and the focus here is that good design makes cheaper and smaller LLMs do stuff that the even bigger language models cannot do, or even other kinds of algorithms cannot do, right? So those design is what we want to understand, and I'm talking about things like reasoning, about planning, chain of thought, etc. And those are the concepts we want to explore. And so I'll give you a few examples. Automated web navigation. And these examples I'm just showing you here, some of the papers, and we don't need to go into detail of any of them. I just show you like what kind of applications have been in the last 2 years appearing that really changed the landscape. Because we're talking about 2 years ago, nobody was talking about LLM agents. So automated web navigation was one of them. It's a difficult task because it's open-ended. We want to build a program that can scrape and navigate websites. It needs to understand what to click on, and the structure of HTML is very complicated. So it's been for a long time like a real complicated challenge task in algorithm design. And then tool usage was probably one of the most revolutionary things, and I really like the name of this paper, the tool former, and it really like started putting the idea out there that LLMs can teach themselves to use tools, right? And now LLMs are being fine-tuned to be able to use JSON to call different tools. And all of you are using ChatGPT, and you see when the web search starts, and all of this results from a tool call in some kind of JSON structure format or something like this. Then another more recent like breakthrough is thinking that any kind of action, because I say LLMs, agents are LLMs that can act. Well, LLMs are good at writing code, right? Because we train them from all the code in the internet. So they know how to write code. And it turns out that they can act through code, right? So they can just create code that they want to execute in some environment, right? And the coded actions frameworks, which we're going to use today, is one of the most powerful out there. They have also been studied in social multi-agent systems. And this is a very influential paper, generative agents, and people are using it. It's reaching really far into the world of philosophy. People are asking questions, what can we learn from these agents interacting with each other about cooperation, about like cooperative games or adversarial games, etc. And lastly, what kind of researcher I would be if I not do a little bit of self-promotion. So this one example from our research, and this is our paper where the rule bottleneck reinforcement learning. Where we're trying to do is it's simultaneously optimized for decision making using reinforcement learning and explainability using the capacities of LLMs. And in particular here, we're applying this problem to assist in the design of public policies. For example, in designing an optimal time of an intervention when there's going to be an extreme weather event. And we're also using it in clinical trials and studies where there's a finite number of resources or wearable devices in our case. It can be assigned to a population of patients. And then we need an explainable policy, but also optimal of how to assign them, right? So this is it for the landscape of research. And I think it's time to start coding. So everyone, this is where you're going to go to the materials, and you're going to open the first tutorial, part 1, okay? So we're going to start in 5 minutes just to give time for people to set it up. If you go to the tutorial repository, you're going to go directly to the GitHub, and there's going to be 3 notebooks. One is a pre-assignment. A second one is going to be part 1, and then part 2. And although I'm hoping that I will not go through the pre-assignment, let me just walk you through it a little bit to what you should have at this moment while you're setting up. Okay. So first of all, in case you're wondering, I did spend a lot of time prompting figures for this course. So we're basically going to need 2 things: the OpenAI API key and the Hugging Face token. And I want to make sure, because I know it's not very well positioned, that you can hear me on the back. Okay. Is there anyone here who wasn't? Anyway, it doesn't matter. I'll go over again. So please do follow the instructions. To summarize here, the most important part is how to add it as a secret in your Colab notebook. And here is the second part that I mentioned, the Hugging Face token, which I assume is the one that most of you won't have ready, but that's going to be for the second part of our tutorial, and we're going to have a break in between. So don't worry, I think you'll have, it's a short break, but I think it'll give you enough time to get this one, okay? Yes, you have to pay. Like $1, but. Yep. Yeah, unfortunately, there's no free tier for ChatGPT itself. Everything we're going to do, it's pretty cheap. Like, it won't be more than a few cents. It won't be $1. I don't think it will be $1, but it's a disadvantage. I'm going to get started. And again, if for some reason you don't have your key ready, don't worry, because the moment you have it, the materials are there, and you can just follow along, okay? So first tutorial, the TLDR says we're going to introduce key conceptual frameworks in LLM agentic systems. Specifically, we're going to talk about chain of thought, React, and we're going to give some examples. And just checking visibility. Is this good in the back? Okay. Right, so first, this is completely unnecessary, but before proceeding, when I work on the notebooks, I like to make a utility function that just brings things in Markdown, and this is just so that when I show you the results of something, it looks a little bit nicer. And it's just initializing the environment, and as it initializes, you'll see that I be connected to a GPU in Colab. I tested this on the smallest possible GPU. What I'm not sure if you're in the free version, if you're going to at some point have some complaints about memory. Probably not for this tutorial, but for the other tutorial, you might have a problem with memory. But just, and also for this one, I think GPU is not even needed. All right, so let's get started. We're gonna work on this framework called Small Agent, and it's very, very recent. It just came out December 2024. It's by Hugging Face, and I am a absolutely big fan of almost everything Hugging Face. And what's really good about this package is that it's very simple. It's perfect for what we're gonna use it today, and all the functionality is pretty clear. And so, and lucky for us, it already installs everything we're gonna need also. So all we need to do is install our small agents library with all the dependencies. And in particular, we'll be using small agents for the agentic part, and it comes pre-installed with Light LLM, and this is where I'm gonna be using to directly call the LLM itself. So instead of the direct OpenAI, I'm using this Light LLM because it's a provider that uses the same API for over 100 different LLMs. So you later want to change to a different LLM. You want to do a ROC instead of OpenAI, which has a free tier, free account, but limitations on the rate. You can do that, or you can do Together AI, like all of them under the same AWS Bedrock API. So pretty convenient. And now what we're going to do is test that we can indeed call the LLM once our installation is complete. Like I said, you can switch providers. There's so many options to choose from. And I will assume that you already have your API key set up in the correct way. And what that means is that here on the menu on the left of Colab, you need to have something that looks like this OpenAI API key for your secret token. And for this first tutorial notebook, we're going to be using ChatGPT 4.0 Mini. It's very powerful and it's very cheap. Okay, so first test. Interesting. This made it very small. So let's this help me. So the first part of this code, and how we're going to do this is I'm going to be reading the code to you basically and running and following along. And if you have questions, like you can stop me at any time, okay? You can leave it to me to decide if the question is better to continue, but just ask your question. And okay, so the first part is all of these APIs, they work well when you have the API key as part of your environment. So we're adding it to our as an environment variable. Directly from the user data function that extracts it from Colab. We're choosing to work with GPT 4.0 Mini, and this is where the fun starts. So let's do our first prompt. So let's all of you that were on the previous session found a little bit repetitive, but let's just ask ChatGPT what is like the kind of message API that it expects us to give at any time. And how do I ask for it? Well, I need to create this list that is each item in the list is a dictionary where we say what is the role, in this case, a system. And I say to the assistant, you are an assistant that loves emojis, and then I ask my question. And here we are. Okay, it worked. I would have freaked out. Okay, so what does it say here? Explain to us how this itself works. We're going to be using these messages all along, so kind of be familiar with it. It says there's three types of roles you can have: a system, a user, and an assistant. You are the user, so every time you ask for a question in the API, you say this is the user asking a question, and every time it returns something, it's going to return it as a dictionary with what the assistant said. And if I'll tell you something that always confused me a lot. Probably 100 people already told you, but LLMs are only autocompleting text, next word, right? And then here it looks like I'm giving a dictionary and returning a dictionary. I found that always very confusing. And part of the tutorial, we're actually going to see how this chat template, like it's transformed into pure text and next token and all this. But for now, just take it as it is. We give it a dictionary and we get back the response. Okay, and now we just need to test that our small agent is working. So here, what would be a task that is hard for an LLM? A very simple task that would be hard is to ask, for example, what is a top Billboard song right now? Why is it a hard question? Because it wasn't trained on recent data. Like, it wasn't trained today. It was trained from a year ago, right? So this is a task that cannot be solved by an LLM alone. This is a task that can be solved by an agent that is capable of taking your question and deciding that it has to go to the web, search the web, read the website, and transform that into an answer. So here we're going to create, we're going to wrap up our ChatGPT 4.0 mini model into this light LLM object. And then we're going to call our first code agent. I'm not explaining you yet how it works, right? This is just to make sure it works. And I'm asking the question, what is the top song right now? And when we run it, this is what we get. The first part we get is the LLM decided that its action is this piece of code that says, I must do web search with this query. So this is produced by the LLM, right? Then it's executed by the LLM, and the LLM receives these results from this web search. So there's already some tool there that knows how to search for a URL and downloads its HTML, right? Then you see here that we get like this log step. So as we said, agents do sequential decision making, right? So now this is just a simple question, but now it's going to be broken down into a series of steps. Like first, I must visit this website. Now what do I need to do? I need to read it. And what do I do next? Do I have the answer yet? So this logs is what we're going to be seeing. It's happening here. Step 2. It try to print the top song info, but it's like this very unstructured piece of text. Ooh. Longer than I remember. In step 3, well, it's not shown here, but what the LLM did is it parsed all of this text, which is really hard to read for a human, but it's easy to read for an LLM, and it's through code, and this looks funny code, but through code it's telling us this is my final answer. So the way this program works is, and this is going to be, we're going to use a similar design when we code our own. By the way, our goal is to code something that does something like this, but to code it from scratch using only the LLM search, the LLM completion API. But this is like a nice way of thinking is whenever the LLM decides to wrap something in final answer, it means, okay, give this to the user after 3 steps. And indeed, you can check the Billboard, and as of yesterday, this was a top song. And it's not perfect. I asked it for the top 5 songs, and it was really hard. it did like 12 steps. It did give me the top 5 songs, but it was like 12, 15 steps. I don't know why I didn't find the information in a single page, but it works. Okay, so here's my little intro to LLM agents, but I'm going to skip part of it because we already talked about it during the intro. But I'll just emphasize this part. Design patterns of LLMs. There's anywhere between 3 to 6, depending what kind of application you have. But for now, the 3 important ones we want to think about is reasoning, tools, and memory. And planning is a little bit part of reasoning too, is subtle difference. But let's think about reasoning, tools, and memory. So we're going to do from scratch, after we see another few examples just for fun, then we're going to code from scratch like this patterns until we can ourselves assemble an agent. And another one of like, each one of these was like 30 minutes of interactive prompting with ChatGPT. But here's my multi-tool usage agent. So there's not a lot of theory, but here's one of those, I will call it a little bit theory parts of the tutorial. What is sequential decision making? Essentially, we start with one observation, which the observation could be the question by the user. What is the top Billboard song? That's observation 0. And in a non-agentic world, the agent would just respond, or the LLM or something, say, OK, here's the answer, right? But in an agentic world, instead, this is going to be a sequential process where the agent is going to take, at each time t, is going to respond with an observation, AT, and then that's going to create a chain of history, and this is going to continue until the final answer action is given, okay? And actions can be internal or external. This is an important concept. From the language point of view, method point of view, we're going to call an internal action something like reason, right? The LLM can decide to take certain reasoning steps, like, step-by-step thinking of what should be the next, before deciding what the answer to the user is going to be. We're going to call that an internal action, thought. But in another example, when we interact with web search, for example, that's a tool that's an external action. And this kind of summarizes it all. We have a little agent that can act on the world. When it acts on the world, it receives an observation back, sometimes a reward signal, and it can perform endlessly thoughts and internal action. All right, so some other few let's go through another 2 fun examples using the small agents library. And after that, we're going to jump into the coding from scratch. So this one we're going to run live, but it's going to have a new thing, okay? I found this one very useful because finding papers in archive is not that easy. And I found this tool just created here kind of convenient, right? So I'm telling here the LLM agent, your task is to help find research papers. That's it, okay? But I also want you to give me the links, and I want you to tell me what the authors are. And it turns out there's no like pre-built tool that does this, right? So I need to code my own tool. And so what we're going to do here is we're going to import from this small agent library this tool function that it's a decorator of a Python function, right? So now we're going to turn our attention to this piece of code here. Everything that is in the screen. What we can see here is we're defining an archive search function. And you see heavily commented. That's actually very important because the documentation here of this function is actually going to go into the agent. That's going to be the instructions that's going to tell the agent how to use this tool. And so it's a little, when we interact with this tool, if I remove the documentation, it's going to say you cannot have this tool. And it's very simple. I say there's a query, search term, number of results, and the piece of code itself here is this kind of thing that I ironically asked ChatGPT for because I don't know them by heart. But there is an API already existing from Archive, and it iterates over its XML structure and returns title abstract link. So this is the tool. This is the part that it's really hard to do, but someone already did, okay? Now the agent needs to know when to use it. So we're going to tell our agent, these are your available tools. A user input tool, a visit web page tool in case you want to follow up. This is going to be useful by the agent because the search is going to only return some URLs and titles. But I want the agent to be able to visit that website, extract who the authors are, the abstract, and report that back to me. So it needs to do like this sequential series. Yeah, question?
Where can you find an articulation of the first two tools that are listed there and what other options are available?
The small agents library.
Okay.
Yeah, there's like very well documented. And there's a lot of examples there too. Like most of my examples are variations of some of the examples there. But the naming I think is pretty good. User input is going to give it the ability to ask me interactively if I want something, visit a website, and then this tool wasn't already there. We just created it, the archive search. And I'm going to be brave and hit go live. So you see here the initial plan. That's the LLM before taking any action, doing an internal action of thinking and saying how the LLM plans to solve this task. It's a prompt in itself. There's going to be a prompt behind that says, before giving the user query, say what's going to be your plan to solve it, and this is what it returns. Now, after doing that, step one, because that was his plan, is asking me with the user input function, the one I imported here, what's the topic that I want to research, right? So any quick suggestion? Outcome prediction, patient, cheese. Okay, I doubt this is going to be any, but okay, let's try. You can see the logs here. There's an updated plan. That's called replanning. And my introduction, I talked about coding as an action in itself. And one of the really powerful concepts of that is that in the initial tool usage, you could only call one tool at a time. But when you can actually call code, you can make a for loop and do an entire search over like different calls of the tool and things like that. So this is a powerful ability of the code as action framework. And anyways, we want to see the result. Was there any cheese in here? So we see number one, enhancing the prediction of disease outcomes. Here's the citation. You can test that all of these links work. Care management, COVID. I don't see any cheese, so I don't know how to rate the answer, but it's pretty matches pretty well the rest of the query.
Is this just raw output from small agents, or are there any?
This is actually a final answer. You can see here. The rest were the logs, but this part is the final answer.
And the logs, like what you see printed, is just coming out of small agents.
All of that is the thinking, yeah, from small agents. That's the agent having a plan, executing one component, replanning until it decides it's time to do the final action. or until it reaches a limit of attempts or etc. So again, we're going to code this from scratch, but I wanted to see how how it works in an already advanced library.
So is there a way to make the answer better if this answer was not right?
If the answer was not right, you can fix your prompt.
Okay.
So that's what we've become in the modern world, right? We are prompt engineers of our agents. We code our agent and then we fight with them for hours, given the right prompt. But again, this is a 12 lines of code prototype, right? Like you can have there's so many designs, agents that call agents, like interactive users, etc. So
essentially, the tool that we code ourselves, what was it forming? What was it?
yeah. So the initial tool was. Let me go back to the logs. Here, archive search. So that's the one thing that it didn't have because, I mean, probably. So archive, the archive repository, for those that don't know, that's where a lot of like machine learning papers are, or papers of all kinds, has already an API that says, I can give you all the papers that are from here. Wikipedia has another one, for example. So of course, the agent could have solved this task just by Googling and then clicking on all the links. But here, we gave it the ability to already print a list, return a list from all the papers in archive that match a topic. That's an API existing from archive. That's why we live in the API world, right? Because all of these API providers now give us tools that the agents can use. Yeah. Oh, sorry. Yeah.
Okay. So what I think the question is, so these are the tools that the LLMs are already familiar with, and
well, this one wasn't, right? Archive search is.
This one wasn't, but still, like archive search is
Yeah.
something in the training set
Yeah.
many years. It's learned from somewhere else.
Yeah.
The question is when it encounters new tools like not archive. Maybe today we do a new like website called whatever archive.
Yeah.
And then this type of search may not be in their training sets, and especially when I realize to ask them to do like API for other LLMs,
yeah,
tend to perform really bad.
Yeah.
You don't understand the latest API set.
No, that's a really good point, and I'll do my brief 1-minute answer on that. You can design agents that read documentation, which is a very common, right? So if you have a new API, they can also read the documentation how to use it. When we're creating the tool, we actually gave it all this explanation of what the tool does, what the arguments are, etc. Right? All of that is part of the internal prompt that the LLM is using, because precisely the goal of the LLM agents is that they are able to do things that were not very familiar in the training. I mean, and of course, there's a limit to what they can do, but we're trying to push that boundary with this design. Okay, and I think I'll move to another example. Let's say like one more quick question.
The agents
Exactly. That's what the library small agents are. It's a collection of internal prompts.
So then if you
Exactly. Yeah, and all of those are parameters. Yeah. Yeah. And again, we'll do our design ourselves. Okay, just one more example. I'm gonna skip over the project creator in the interest of time, but I'll do the Robo Wrangler. Okay, an assistant for data operations, and of course, again, this is a reduced example, but I want you to see here is that we can also have external objects. In this case, there are these two data sets: the customer ID and the orders, the customer data set and the orders data set, okay? And what I'm going to ask this agent is to help me assist with data wrangling and visualizations, and based on these two data sets. And I'm asking it to inspect the data sets to understand, and here rather than use a user input tool, I already gave it my query. I could have, of course, do an interactive query system. But I say create the bar chart of order amounts by customer name. And why could this be a little bit difficult? Well, because first we see that the names in these data sets do not exactly match with each other. So I got a little bit smart on like, okay, understand the concept of customer ID, or even if like the name of the column is a little bit different. And another thing in the design of these agents is that it's by the end of this tutorial, we're going to talk a little bit about safety, only one, just very briefly. But here, one of the safety mechanisms that we need to have is because they can execute any code, and that's very dangerous. We're only telling it, what libraries is it allowed to use. And it even has tools built in to use like Docker or sandbox environment that are more safe, that are not turned on by default. And okay, so here's my question. And this was not interactive. I'll just show you the outcome. But here's an important part, actually, that I want to show you. When I run the agent, I pass as arguments those two data sets, right? So I'm telling in this case, I'm telling the design, there is this external object that you can use that is not inside the system. So this would be, if you think of how you interact with ChatGPT, think when you are uploading a file and you're asking ChatGPT to do things about this file, like ChatGPT on its own is no longer just an LLM for predicting next words, right? ChatGPT, when you interact with it, it already has a lot of agentic features built in, and it's not very different to how this one works here, right? Like we're now giving it an external source of information. Yeah.
Does this transfer the entire content of those pandas data frames or just the metadata? And I'm asking in the context of situations where this is running on the Google server.
Right.
Maybe you have a large repository of data that's sent somewhere else.
Yeah, very good question. So here, it passed the entire thing. In fact, you can see here that the new run says these are the inputs, okay? Here, and this is the first part of how my original prompt was translated, and what the software did is put the entire data as part of the text, which is not an optimal solution, right?
I wish that it's small.
Because it's small. But of course, if it's big, I can have a tool that it reads from a CSV, from a Parquet file, from a database, and I only would need to pass the location of the file, and then as a tool, it will already read it, part of it. So, and that's possible too. I just didn't want to. I wanted to save one more tool. But yes, that's a really good question about the design. Okay, and long story short, the real incredible thing of this is that completely on its own, because we allowed it to use everything in pandas. So before the era of code agent tools, we would have need to design a series of many tools, like merge is a tool, plot is a tool. But now we gave it the entire library of pandas as possible actions to do. And so it's using all of them, and here it is. This is actually the correct plot produced by this. So you can imagine why a lot of people in a data visualization would be interested in agents, right? Okay. So that would be the part of our examples here. Just take one more question, and then we'll go to understanding the core.
In this example,
yeah.
In this example, what is the LLM doing and what is the agent doing?
Okay, so I think it's worth spending 1 minute reviewing that. So let's go through the logs, okay? So this is a task that gets created, the prompt, the initial prompt. Again, we're not seeing all the internal prompts, right? But there's one internal prompt that first says, make a plan to solve this, and here is the initial answer. Then once that is done, there's another prompt that says, okay, now start following your plan. Start with step 1. What action do you take to solve step 1? And then so here's a step one, and then this is what the LLM returns. It returns this piece of code. This itself is just code, right? At this point, it's nothing else. But then itself code is a tool. So what the code is going to do, we're now going to internally, the program, small agents, is going to send that to a code interpreter that is going to parse this piece of text, and it's going to execute it in the current environment. Right? So any piece of text can be sent to your local environment or a sandbox environment, etc. So that's what's happening. And then once it runs this part, it returns. This is the new observation. You remember observation, action, observation. This is the new observation, the result from doing this first operation. And then the LLM says that there's another internal prompt that says, okay, given this observation, continue with your plan, right? So this goes on sequentially until there's a point at which the LLM decides, by looking at all the previous history of actions and observations, I'm done. And you can see that at the end, final answer. It says, here's where I saved the file, which we also saw printed, but this is where I saved it. And it's actually saved. You can check. Right? So that's what's doing.
Would it be accurate to say that the agents are within context?
Yes, but another way to say it is how we define it in our initial slides. There's a computer program whose flow is being controlled by the LLM, right? That's a small agent's definition, by the way. Mine is like LLMs that act, but the control of the flow is the one in the small agents library. Okay, I think I should just move on in the interest of like finishing with understanding the core. So here we're going to do, we're not going to do this point number 4, I'm sorry, but we're going to do 1, 2, 3. We're going to do chain of thought, which is the main tool being here used. And then we're going to talk about React, which is translating chain of thought in an interactive environment. And these are like superly highly cited papers, and they're basically the core component of almost every agent library. And in itself, you'll be surprised that there's so famous papers because the idea is so simple, right? But it's well executed and well explained. And so here's the key idea of chain of thought. LLMs are trained for next word prediction, but we can query them in smart ways, right? So in this example, there is a mathematical question. Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many balls does he have, right? And the LLM said the answer is 11. And actually, I don't know if it's correct. I didn't do the math. But yes, it's correct. But here's another question where the answer is incorrect. So what I'm trying to illustrate here is that the LLM is actually pretty bad, and we're going to see examples ourselves too. I just saw just giving you the answer. This is because they're just predicting the next word. Like they don't have a concept of arithmetic built in, right? However, because they've seen many numbers in the past, it's easier for them if they just do a more verbose answer and they take it step by step, right? So literally, all that chain of thought is writing your prompt, and at the end of your prompt writing, solve it step by step. That's it. That's the invention of the century. Adding solve it step by step at the end of your prompt. But it changes everything. Right? What we see here is like, why do we bother at all with chain of thought? And what you're going to see here is like these are 4 benchmark data sets. And what we see on the x-axis is the size in billions of the language models. And like, something like the modern ChatGPT has like 1.5 trillion. But even 1 year ago, 500 was the state of the art in terms of like model size. And blue line, chain of thought, is going up. Like actually, all of them are going up. But what we can see here is that standard prompting its maximum level at 500 billion parameters, a much smaller LLM using chain of thought can do better, right? So this is that message I was saying. Good prompting or good design leads to smaller LLMs outperforming the much larger and costly LLMs. Okay, so let's test it ourselves to see that, what they say is true. And here's a pretty nice example. Oh, I should have not run it because things never work live. But here it is. Here's a question. It says, how many times is P negated in the following formula? And there's just a lot of these like negation formulas. You could have changed for any symbol actually there, but the point here is LLMs are really bad at counting. Like even the good LLMs, they don't do good at just counting how many times something appears. But for us, it's really easy because there are blocks of 5, so like 6 blocks of 5, 30, and 2, 32. Like we can do it visually really easy, right? Here the font doesn't help, but there's each one of those blocks is like 5 of those tildes, okay? And you can run it again, actually, and sometimes it will give the right answer, sometimes, but very often it will not. And 6, okay, completely out, like, because it counted 6 blocks, you see, like, believe it or not, there's one paper called Self-Consistency that is also an influential paper. It like says do it this 10 times, and if all the times like just grab the ones that is more often appearing, and okay, that works. But anyways, okay, but can we fix it with chain of thought? And then what we're going to do here is, and by the way, I said that chain of thought is just asking the LLM to say solve it step by step at the end. But I'm actually going to do it a little bit differently, more like a real chain. And I want to do this way on purpose because that's going to make it so easy to then transition to the React loop, okay? So instead of just saying do step by step on the same query, I'm going to say solve one step at a time per answer. More like we saw the small agent solving the task, right? So here is a function called chain of thought loop. And we're talking about this before. There's this internal prompt that's going to be called several times. And this internal prompt is a function of the original problem, the original prompt. But it's going to say, break down the problem in simple steps until you find a solution. Then begin each step with a tag thought. This is just for visual purposes. And each one should be just a simple computation or a simple strategy. And once found, indicate your solution with the tag final answer. So you see, I kind of copy a little bit the design of like final until you are happy with final answer. And of course, I didn't come up with this at the first trial. I actually had to design this prompt for a few rounds. And here we have a loop. While you don't reach the max steps. And check this out. This is an important part of the design. We're going to have this object here called memory. And essentially, everything that's going to come out from the LLM, we're just going to be, and from the prompts and from the LLM, we're going to be appending it into this memory. Okay? And this memory itself is going to make the internal prompt because you already have the instructions and the previous observations. We call inside the loop the LLM. We obtain the response, we append the response to the memory, and we check whether it contains final answer in the observation, right? So we're just looping until it wants to tell us the final answer. Here's the conversation, we call the loop, and we see something like this. Here at the top was just the original question. And then it decided to do what? 5 steps. First one just says it's more like a plan, right? Like strategy. I notice there are multiple groups. I will need to count all the individuals. I'll focus on the group of tilde separately. So it decided to focus separately And then it made some computations like the ones I made visually, like, oh, there are 6 groups of 5, 30, and 2 on the last. And then lastly, it gave the correct answer, right? So that's cool. We made it answer correctly just by doing this kind of agentic loop, right? All right, so do you have any questions about the chain of thought? So simple, right? Okay, just for the fun, does it work? It works now more often than not, but not all the time. You see? Of course, the notebook that I pushed to the repository has the perfect answer. But 2 times in a row, bad. I actually not seen it do wrong so many times. But anyways, I feel disappointed right now. I promise you, it works. Yes, fix the prompt. Anyway, oof, that's wrong. Okay, sorry. That's why you never do like, you know, it's like a live product where the iPhone breaks, it doesn't turn on or something.
You took the temperature when you were designing this agent.
Good point. I'm using the default, but you might want to use like just like best answer or something. Depends on what you want, but yeah.
Can you give him some hint? Let's say it cannot be greater than 500.
Of course, I designed this chain of thought loop in a way that it works for any problem. Like if you see how I design it, I'm not saying, oh, your job is to count tildes, right? It's a function of the problem. But of course, like if you're solving a problem, you know what your problem is, and you don't want, you know, like you're not going to build the next small agents library. You just want to solve your problem. Then you can give it as many hints as you can, or you can add in your function something that's additional hints or something that you can add.
Like a few shots.
Exactly, and that's very important because we do that in another part. Okay. All right. So now let's move to React. Okay. React says, okay, chain of thought is great, but chain of thought doesn't know how to use tools, how to use action. It's not designed for an interactive environment. It's just mathematics problem solving or problem solving technique. So let's now move to the interactive world and view how like the React loop would work, right? So I have at least like 3 versions of this. We have a task. We add it to the memory. Is it final? It's not going to be final at first, right? But is it final? No. We call the LLM, and we have thoughts, but we have 2 new things, tools and action, not only thoughts. And then we're going to execute those actions, observe the response, and go back, right? So this is pretty much a small agent we were using. And this is in the literature called like the React loop. And it's called React because it's reasoning plus act. So here is the example from the React paper, actually. The question here is, aside from the Apple remote, what other device can control the program Apple remote was originally designed to interact with? It's a hard question like the Billboard question we asked, right? Because it requires researching something that might not be just very easily out there in the memory of like the pre-training or something. Long story short, if you only applied chain of thought, you're relying entirely on the pre-training, and then it will do something like, oh, Apple remote was originally designed for TV, to TV, blah, 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 iPhone, iPad, or whatever. Like, this is wrong. But the React agent has intermittent loops of thought and actions, right? So it decided to do the search. It has a tool called search. So it can search for Apple remote. This is what came out of the search, a Google search or something. And then thought to search now, search for this other element I'm still trying to figure out, search for this other element, etc., until finish, like I'm happy. This is what it was designed for, right? So after we already saw small agents, it doesn't sound like something new because actually this is how it's built. So to summarize, when we have tools available, it expands the universe of what is possible. And is that, okay, and then coding React agents can perform so many actions, and React action is the analog of chain of thought. Sorry, I stopped 1 second because I wanted to show you this. Visualization from I actually got this from the Small Agents website, but it illustrates this what we're doing in the same diagram I showed you, but in a nice way I could not replicate. Right? Memory increment, we run LLM, new LLM output, parse, and this is actually surprisingly hard when we code it, but parse what we need from the LLM, execute it, etc. Right? So what we want to do now, and this is the last bit of this first part of the tutorial, is code this. So we're going to start with this first design called tool calling agent. We're going to have two designs, like the tool calling agent and the code agent, okay? So the tool calling agent, we're going to remember how we created our archive tool, right? Like archive search. So now in the tool framework, actually there needs to be like a well-defined tool for everything we need to do. So here I did a very boring thing of coding a calculator, right? I just give it two numbers and say, here's the operation you want to do. So there's not rocket science here. It's a really boring operation for what to do with A, B, and say add, subtract, multiply, whatever. But here is a little bit more interesting part, right? I'm creating this object called function definition. And the syntax, I actually took it from the Meta Llama documentation. So internally, this is the way they use the function tool documentation. So there's ways in which you can interact with the Llama LLM to use tools, and this is how you have to give it to them. So that's why I did it in the same way. And this is a JSON, and you have to say the name of the function, the description, type of object, the parameters were required or not, etc. So this is all the information that the LLM needs to know how to use this tool, right? So of course this feels like an overkill for like a simple operation, right? But and then we saw like we need to parse somehow when an LLM tells you to use a tool, right? So here I say, okay, if you see the tag tool, then do a little bit of like string manipulation, basically, so that you just tell me basically parse what is how I need to call the function from pure strings. So again, this is a string manipulation, nothing particularly interesting, except that it takes a string and it returns something that's already parsed in a dictionary using the JSON format. And lastly, this is the interesting part. This is the React reasoning with tools loop, right? So just like we had our chain of thought, here is from scratch. So what I mean from scratch is only allowing us to take a prompt and a response, nothing else, how to use a React agent. And so here are the instructions. And similar to before, break the problem in simple steps. Response must consider thought, tool, final answer. Then we allow now for a tool step. You may use exactly one tool, starting with the token tool, followed by a tool call in the JSON format from the function definition. So I'm saying from this object up there, which is dynamic, right? Like for every problem, it's going to be a different function definition. We insert that as a template so that you have a different problem, you can have a different function definition. And these are the rules of the game. This is how you're going to do your the loop we saw in all the small agents example. And finally, this got to look pretty familiar. There's a memory, and then we execute the loop pretty much the same as before, adding to the memory. We just have this new line saying, if you see the tool usage here, parse it. And there's a nice new feature here we didn't see before that says if there's an error, just correct it. All right, so the chain of thought failed me. I hope that this one doesn't fail me on the live demo. Oh, that's just my bad. I think I should have run this first. Oh, by the way, I skipped this before, but this was to show you that chain of thought is pretty bad at this arithmetic problem. Multiply the square roots of two numbers. And this is not surprising because these are words to an LLM, right? They don't have numerical meaning. So multiplying them when it's not small numbers is pretty hard. And it does its best. Actually, with chain of thought, it does a lot of operations. And, you know, it tries, but pretty bad. OK, so now let's see if the React loop can do this a little bit better. It should, as long as it can call the calculator, right? And did it work? Whew, OK. One demo that worked, perfect. Right, so we see what happened here. There's a thought to solve the problem. I need to find the square roots. That's a strategy. Then, and first I will call the square root. So it decided to first call the square root of one number. And here's the result. That goes into memory. New thought. I need the other number. That goes into memory. And then last operation, I need to multiply again, call the calculator. Here's the JSON tool result. And it decided that's the final answer. So pretty clean. And lastly, this is the really last bit of the tutorial. Our calculator tool was an overkill, right? Like it wasn't very pleasant to define how to add two numbers. So can we like expand our universe of possibilities by asking it to produce the code in any Python format that we want to execute? And so let's see. Funny enough, I don't need this here because I'm not using tools. Oh, no, that's not true. I don't know why I did this way. But you see we had a really complicated tool definitions. I changed it from you must only use the math module for calculation. So the math library in Python. And that's optional. But basically what I wanted to translate, remember when we saw the data wrangler, I told it only use pandas and matplotlib. So that's kind of a little bit what I wanted to insert here in the design. Say these are the valid libraries you can use. And then here's the code coding agent. We no longer have a tool tag. We have a code tag. And here's a new nice thing. Execute code block, right? So the LLM returns here observation, right? And if the observation is interpreted as code, it goes to reverse this parse code, which all it does is remove the spaces at the beginning, at the end, and the markdown, but it's essentially just cleaning up a little bit. And then it goes into this function called execute. That's a built-in Python function that interprets Python code as a string, and it executes it in the environment, right? So we pass in these local variables, and basically all of the computations that happen when execute is called are actually saved here, right? So if inside the code I define final answer, there's going to be an object called final answer, right? So that's a little bit of like the magic behind this execute sandbox. And so here we say if we see the final answer in the local variables, return. Otherwise, just keep in the loop as before.
I lost the thread here just a little bit. That code is executing on the OpenAI server?
No, this is executed in R.
On the Colab host machine?
Yeah. So if it was your computer, it would be on your computer, and here is in Google Colab, right? Which is the same thing done by the small agents, right? The LLM is just telling us the auto-completion from the prompt, but the execution is in our environment.
What's the second argument in the X section?
That's called a global variable. It's a little bit technical even for me. but it's basically saying what things from outside it can be able to use inside. So if we had a data frame or something, we would need to declare it here. It is also a safety feature, right? So that it doesn't execute, doesn't use malign. And in any case, this is the final answer. We no longer need so many operations. We have an initial thought as before, and this is what the LLM returned. It said, I want to do import math and do this calculation, right? Everything is the same code, like this is a square root, final solution. Then the code result, this is what came out from the execute function, or from the local variables, actually. That's what I printed, final answer. So I find this like pretty amazing. Because like, right, we didn't define this just for math, right? Like, so we can use the same loop for other problems. And so to wrap up this part, we have only touched the surface. And there's so many next things you can do, try a more sophisticated system. There are problems in which you'll need a huge memory, like there are gonna be just many steps. And all of that keep getting like stacked in a really long prompt. So there are other techniques called like retrieval augmented generation that if you were in the previous tutorial, I think you covered. You can use those techniques to inside the loop to improve how the memory is used. Then I only talk about chain of thought, but there's things called tree of thoughts, for example, where there's like different paths of thinking you can follow. All of these are design patterns. And this is a slide from Deep Learning AI. Basically, it's just showing that this is, again, these are human evaluation mathematical tasks. And GPT 3.5, if you just treat a mathematical answer, like answer a question, is way worse than GPT-4. But when you equip it with all these different agentic frameworks, that all of those are just improved versions of our loop, they're just as good, and both of them are almost perfect, right? So we went from 50% to almost 100% by just using this way of prompting. With fake Chinese characters. And so the long story short here is, I need to turn this on. I don't even know if it's that helpful for it. The long story short here is we saw like this chain of thought, React loop, and these are very powerful tools, but they don't always solve the problem, right? And they just make it more expensive. So we're gonna take here a perpendicular direction, and we're gonna talk about how can we learn to learn, I call it that way, but reality what I mean is how can we fine tune or improve the LLMs themselves to be better at a specific task. And this is what sometimes we call grounding, okay? Finish session 1. And I really hope that you have your HF token. But then again, you can, these notebooks are going to be there. If you don't run them now, you can run them later. So don't worry about that. And for this one, it's very likely that you need the Colab Pro, not the expensive one, the $10 monthly one, and it doesn't use a lot, but it's just the memory is right, at the border. And just to give you a little, well, I'll get to that, but we're almost at the point that it fits on the free, but I feel like it just needs to be this more efficient. Okay, so I cheated a little bit here because since we're gonna learn in the sense of neural networks, things take time. So I'm gonna download from the repo some checkpoints that I'm gonna be using just that the results show faster, but you can rerun everything. And in here, the main tools we're going to be using, PyTorch. And I mean, if you're not familiar with PyTorch, I will explain everything. But you know, like I said, this is hands dirty, so the technical level is going to be a little bit more challenging. But PyTorch is the main tool, at least in research, for neural networks, and we're going to use it. And then also, a neural network is just a neural network, right? So we're going to treat it as just a neural network, a really big one, and we're going to use PyTorch. And then we're going to use tools from the Hugging Face ecosystem. Essentially, we're going to be using two tools or three libraries. Transformers. That's like the main one. That's where transformers is the type of architecture in neural networks, and basically, like practically all of the big LLMs right now, all of the main ones are transformers. So this library we're going to be using, and parameter efficient fine tuning, because you cannot train these ones in a normal way because they're really big, and that's it. Okay, and what's going to be our task here? Actually, in the previous tutorial, we had like a lot of tasks. Here, we're actually going to focus all the time in just one task. This is a game that I started trying to solve in my PhD, where there wasn't LLMs, and it seemed super hard, and now it seems easy with the LLM tools. It's called Text World, and you're going to see examples, but it's not that I want you to play video games, but like any problem in an interactive environment, not any, but many problems, even the ones in social impact that I'm researching, can be translated to a text-based environment where you represent the state of the problem through text and action through text. So by trying to solve Text World, we're actually providing a recipe to solve many real problems, okay? But I use Text World because it's very well controlled. And how Text World works is we're going to be in a virtual world that has different maps, rooms, objects, furniture, doors, etc. And there's different flavors of that game, but we're going to be using one where the agent needs to pick up stuff that doesn't belong to a room, okay? So we're going to be playing the common sense game. So I'll show you in a minute those, but we're going to install basically our two dependencies here, Transformers and Text World Express. And Transformers itself, we got the options to PyTorch and accelerated training. And we're going to be using a MetaLlama 1 billion model instruct. So first question, is this a big or is this a small model?
Small.
1 billion is small. This is the area in which we're living. So it's funny because it's an LLM, but it's now being called a small language model. But this is bigger than anything that existed like 4 years ago, right? Or maybe not 4 or 5 years ago, right? So it's like, okay, it's the smallest large language model, right? But one thing that the first thing you got to learn is that we can use very big language models, but if we want to train them ourselves, actually, because of the computation resources, we can only like comfortably work with smaller ones. Like 1 billion is very small and not very capable, but it's fast. And probably like if you work with a cluster with a really big GPU, like you can find you in a 70 billion model, but it's really hard, like without specialized, very, very specialized software to try to go above that range. But even for this 1 billion model, we'll see that we need specialized techniques like parameter efficient training. And here in testing that I have the Hugging Face token. Again, what that translates to is you went to the Hugging Face website and you added here something called the HF token, and that's in the pre-assignment notebook. Right, so I'm going to test here. Let's see what's going on here. I have this MetaLlama 3.2 1 billion model instruct. Instruct just means that has been fine-tuned already in Llama for answering my queries in question answer setting and not just autocomplete next word from the entire internet so wildly. So it's better for agentic usage. And here's the main way we download a model. Transformers auto model from causal language model. Don't worry about the causal part. We give it the ID. And all this configuration already starts seeming a little bit daunting. We're saying, oh, we're going to use float 16 numbers, which is a reduced way to represent the numbers in the computer. There's ways to do it even in 8 bits and 4 bits. But for the smaller language models, doesn't make necessarily that necessary. And we have another object here called the tokenizer, right? So that's kind of new. We'll see how it works, but it's essentially the function that goes from text to the representation of tokens or words as integers, right? And all right, so let's run it. And just before we run it, here's a nice function that we're going to be using all over that wraps up the entire process of calling an LLM, right? So I call this function call model. I give it only the prompt and only the model. So this is the standard basic functionality that we had from Light LLM in the other version, but now we're not asking an LLM in like a remote server. We're going to ask an LLM that we have downloaded as a file. So this is how we interact with that model, or I guess it's a file that gets loaded into a neural network object, and then it's how we interact with it. And it says, take the tokenizer and take that message style that we were using before and apply a chat template. So every provider, Meta, what's another provider? Anyway, like ChatGPT, Meta, like all the providers have their different templates that they use, and the Transformers library makes sure that we have the right ones in the moment we download it with this auto tokenizer, and you're going to see what this means at generation. And basically, our model that we downloaded is going to have this generate function built in that we're just calling it with some specifications. People already asked me about temperature and things like that. All of that goes here. And okay, so probably scared you already, but you don't have to be scared of this function because all it is just it's an abstraction of what we already had in the previous tutorial. Call the LLM and give me the answer, okay? And it's pretty well documented in the Hugging Face, and it's a pretty standard way to do it. And I'm running it to test it. And I'm going to ask a dumb question, not dumb, but like, what is the capital of France, okay? But I think it will be helpful that we look at how this function works internally just to understand the whole rest of how we're going to fine-tune. So this model weights are being downloaded right now automatically, and it's 2.5 gigabytes. The tokenizer is being downloaded. It's a JSON, it's a dictionary that says how things are mapped. And here I have a print function above it. So it confirms that our LLM has 1.2 billion parameters promised. Memory footprint is 2.3 gigabytes once loaded in memory. And check out the template. This is the craziest thing, because I didn't know this when I started working with LLMs. We just asked the question, what is the capital of France? But this is what the model receives. This happens when you send it to the API. There are these special markers called, I guess, special tokens, okay? So just like I was using these brackets, action, brackets, thought, like these are special tokens that say, there's a header, which this is not important. It just says, what's the latest model? But this is where the actual thing starts here. It says start header ID user. So remember that dictionary that says role user, role assistant. This is how it gets translated into this piece of text that says, okay, this is what the user says, what's the capital of France, end of his text or their text, and then start header ID assistant, because now the assistant is going to respond, right? So the assistant needs to know the queue. You're giving it the queue that's going to start printing the next token. So assistant starts, and here's where it ends, right? And the assistant's going to auto-complete the rest with going token by token, next token prediction. Of course, this is LLM agent scores, not LLMs, but I think it was useful because it's going to be important on how we fine-tune them. And here is this representation of the same text, but as a sequence of integers, and these are the IDs, right? So this thing gets broken into tokens that are almost words, but sometimes are pieces of words, and each one maps to one of these integers. And here's the answer again by the LLM once we use the generate. You can see that it generates an object of type tensor. All of the objects of PyTorch are tensors. It lives on the GPU. It says here CUDA, that's where it does. And this gets back to the tokenizer with the decode function of the tokenizer, and we get back the end. All right, so that was just like the quick breakdown of what's happening when we call the LLM that we just downloaded. Now let's look at the game we're going to play or solve. Text rule common sense, and it's a test that tests the ability of an agent to have a notion of common sense. So this used to be a really hard task in the past before LLMs, because before LLMs, the way natural language processing worked is we need to have a huge database of examples, pairs, and eventually it learns to recognize positive sentiment or negative sentiment or whatever. And embeddings improved a lot of that, but even then with embeddings, still like common sense was a little bit challenging, but with LLMs it's becoming easier. And the task here is if you find a dirty object or something that doesn't belong in a room, pick it up and take it to the room where it must be. So if I find a dirty dish in the living room, the agent has to choose to pick it up, has to choose to navigate to the kitchen, and then has to drop it in the kitchen. And then it's going to get a point or a reward every time it performs this correctly. So here we're loading the game. We have an environment factory. Environment is a common way to call these games or in the sequential decision making. We create the environment with time limit, number of locations, doors, number of items to put away. And here I want to illustrate, I call it history, I should have called it memory. That would have been, later I call it memory, but history was more common in the game. But here's an example of just one decision step, okay? Is we start, we say, hey, welcome to text rule. Here's the task. The task is going to be the explanation of pick up things. Initial observation that came from starting the new game. Now for every step, here I'm just saying random choice because I'm not yet using the LLM, but I'm going to replace it with an LLM choice later. Take the action. It's called stepping in the environment. And then append the result to the environment, right? Right, so I just want you to look at this like logs to see how, imagine these are the logs that we had from small agents, but now of this game. Again, there's no agent here smart, this is just random actions in this environment. Here's your task. You are in the pantry. In one part of the room, you see a folding chair. It has nothing on it. To the east, you see a closed plain door. These are the valid actions. By the way, I'm giving it the valid actions because it makes it so much easier. But there's a version of this game that is very challenging where you don't tell it anything. Action closed door to east. That is already closed as the game. No reward. And just keep playing. Now there's some commands like look around that repeat some of the information or even more that you didn't have before. When you move east, for example, now you're in a new location. Now you're in the kitchen and it tells you what you see at the new location. You have an inventory that you can check if you already picked up an object, etc. So this is the game that we're going to try to solve, okay? And am I right that the random action didn't do anything correctly here? 0, 0, 0. Okay, let me just rerun to see if we can get the random action to get 1 point. A negative point. Okay, so that was something bad. Let's see what happened here. I think we're in the kitchen. I'll put clean plate in folding chair. Okay, so that was wrong. So instead of cleaning, we're putting the object where it doesn't belong, and then so we're paying a penalty. All right, so step number 1. Can we apply what we learned of React agent or the chain of thought, like step-by-step reasoning, and see how, first of all, like if we just ask the LLM, what do you want to do? How does that do in this game? And then if we additionally ask it to do step-by-step reasoning, how will it do in this environment? And keep in mind, a 1 billion model is a very bad model. However, the improvement that, like, I tried to do this last year with the best 1 billion model of last year, and it was just absolutely like nonsense. Actually, this year, like with because the 3.2 we're using, Metalama is quite new. There's been a really huge improvement in those like really small large language models, which is very exciting in industry because you can put them now on robots, on devices, right? So we're reaching that point. This will be the kind of model that when you have like a robot dog, it's going to be used to talk to you. A robotic pet. Okay, so what we're going to do is code the task prompt, code a function to generate a plan, code a function that selects the next action, and then this is a very tricky part. These models return a lot of times like things like, I think you should move east. And then it's kind of hard because that's not understood by the game, you know. And just going from I think you should move east to move is actually pretty hard. So we're going to use another LLM to help us with that. And which, by the way, going back to the idea of like LLM using tools, you can think about it as another one of the options that the agent has when something doesn't work is called another agent that helps parse the answer, right? So we're not explicitly coding it this way like this, but that's the idea of orchestrating agents. And all right, so there's not a lot here to explain besides like a lot of prompts. This makes a task prompt. Again, I try to code this as general as possible so that if you give me a different game, it will make sense. So it doesn't say anything about here necessarily about, oh, maybe here I cheated. My task is to move misplaced objects. That's an example. But originally, it was an input to the function. I just made things easier. But in general, the design pattern here, except for any potential example, is in a way that you can do for different games and different tasks. All right, so planning step is just outline a plan to solve the task. Action step is, in addition to the task prompt, which was just a representation of the memory. Okay, actually, let me start from scratch again. Task prompt, I'm just taking the memory and putting it together, joining it in a big string and saying, answer the questions below. That's it. For the action, I'm just saying, take that as a starting point, make a plan. For the action step, I'm saying, here's a task prompt. Now let's decide what's the next, before taking the next action, decide what is the right idea. That's the thinking part, was a good strategy. And then I'm calling the model, sorry, down here with another one that says just choose exactly one valid action from the valid action list. And lastly, the function that says extract the valid action, again, is just a prompt with here a lot of examples. This kind of examples is, if you remember what we did function definitions, for example, that was a way to give something to the system that we wanted to do. you can design a general purpose ejecting system, but all of these are options that the user passes to direct the system. Okay, so this is it. Let's hope it works. And moment of truth. First, let's test it in one single decision step. So here now we see the chain of thought. The agent said, you see the teapot on the table in front of you. Action said, move west, makes no sense. That's, again, it's a 1 billion model. No reward. And do it now. Let's play a full episode, and all I'm gonna do, there's zero magic here, is do this loop, but do this in a loop until the game is over. So basically here, reset the game, start the memory, initialize the task prompt, make a plan optionally, and while not done, update the task prompt, get an action, execute it in the environment, update the memory, loop, 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 until the game is done. Return all the collected data and the reward. So if you've ever done reinforcement learning, for example, this is just the basic way in which you do the reinforcement learning loop. And all right, so let's play one episode. Playing. All right, so did it do anything smart? Let's find out. Right, so here's a task, turning observation, around. My task is to pick objects, that's a thought, then place them in their usual locations. Okay, at least it's repeating the intention. My action, you see, like here, all of this is like the thoughts. It says, I will pick up the waste paper basket. Okay, so this actually makes no sense, waste paper basket. I don't know what this got sent, take notebook. I think this was just the other LLM not understanding what should happen here. And then, but the notebook was the right thing. Okay, that was just. But I would hope that these random things, here made a mistake, put back the coffee, so you get penalized. So you can have fun looking at these logs. But then the moment of truth is, if we do this over several episodes, how bad or how good will it do, right? And then, will it help or will it not at this immediate thinking step? So do you want to bet? So can you raise your hand if you think that asking it to think before taking the action will improve? Raise your hand if you think it will improve. All of you are convinced? Okay. Pretty universal. So you do believe in chain of thought.
But will taking into account the reward or not?
We're adding the reward. Okay, that's a very good question. Actually, it's a deep question. We're adding to the memory the previous reward history, right? So actually, the agent, when it takes the next decision, can look at the past history of decision. So it's doing something that has a fancy name, like in-context learning. So it can actually look from the history what things worked and what things didn't. What things didn't. Of course, this 1 billion model is not pretty good at it. But if we were using another model, it could learn a little bit. That being said, in-context learning is not always very good or sufficient in reinforcement learning, but or in this kind of interactive settings. But it's a good question. So yes, in theory, it is taking into account how the reward was given in the past because it can see all the logs. Okay, so, and did I run? Okay, I think I need to run this. And this is me cheating. Uncomment this to rerun everything. It should take about 20 minutes to run this part. But I'm gonna load the results here. And of course, the plot's already there, but okay. So those of you that think that thinking helps, good news is that thinking helps. So keep thinking. Okay, but is this really good? So can we still do better, right? Can we still improve it more? So far, we've not done any grounding. I just reapplied what we already saw in notebook part number 1 to this new game. But now we're going to start with end with a model that we got from Hugging Face that we have the weights, right? So now let's see if by using data we can improve the neural network and make this work better. Okay. So supervised fine-tuning and low-rank adaptation. So here's the learning plan. That's our learning plan. Set up the LLM for efficient training using LoRa, Peft. In supervised fine-tuning, we assume there's experts that give us some like good data. So I also choose TextWorld because it has this function called gold path. So I'm generate a few gold paths that are greedily obtained to be like semi-optimal answers from the game. This is done in like brute search, but it's a somewhat simpler game. So there are already these gold paths that I can extract from it. And what I want to see is if by using these demonstrations of correct expert actions, I can teach my original LLM to be more correct. And so that's what we're going to do, okay? And of course, a lot of content here, but here's the primer on how LoRa is going to work. So first of all, just a reminder, what is a transformer in a very conceptual way. A transformer takes input a sequence of tokens that gets encoded, of course, as a sequence of integers, and then gets mapped to a sequence of embeddings. And then that goes, something called positional embeddings is added to it, just as what part of the sentence you're in. And then goes through complicated neural network made of combinations or sequences of mass self-attention, feed-forward neural networks. And these are called decoder layers. And you don't really need to know how that works. The only thing you need to know is that attention is all you need. And you get the output token embeddings. And we're going to interpret these output token embeddings. We're going to go through a last layer. And anyways, out of all of this, what we're going to get is at each one of the input locations, we're going to get a prediction of a probability for the next token, right? That's what we're going to get. A vector that says the probability of the next word. LLMs are cool functions. Like we're going to get a probability for the word functions, a probability for the word objects, etc. Right? That's my, sorry, humble explanation. But how they are trained is we have the actual next token and we have the predicted next token. So they are combined to compute a loss function, and that loss function is called the cross entropy loss. But essentially, it's you have less loss if you had a good guess, you have more loss if you have a bad guess. That's it. And so that was a quick rundown. And then this is where it starts getting interesting. Many of you maybe have heard of fine-tuning, right? So fine-tuning happens with a model that's already trained, where we have a new data set, and we can train it a little bit more to work better for the new data set. And there's two classic approaches. Last layer tuning, where we add another layer, like we remove the last layer that we add another one. And this is the classic way things were done, for most of machine learning courses is what you learn and still used a lot. And then there's full fine-tuning where you're very lucky and you have a lot of new data and you just retrain your whole network, but you still get some benefits from having started with something trained. And when you have enough data, full fine-tuning works a lot better. But then enters LoRa, okay? And I have no good explanation for putting some parrots here, except that in Spanish, parrot is loro, so that's a little bit like that. Anyways, it's a terrible joke. But LoRa takes the best of both regimes. Like you can think it of an in-between full fine-tuning and last layer fine-tuning between like a lot of parameters and few parameters, right? And it's really one of like the great inventions that's allowing to train like fine-tune these like large language models. And there's many variations of it, quantized, non-quantized, or what QLoRa or whatever, all these names, but all work somewhat similarly, and the idea is like this. The decoder layers of our neural networks are just made of weights, and the weights are matrices based. So what a neural network is an architecture of how to do computations and a huge collection of tons of matrices that we call the weights. And each one of these matrices, when you fine tune, you have to change the matrix. That's what you do to make a better matrix, right? So in LoRa, instead of like, or in general in adapters, in parameter efficient fine tuning, instead of like changing the whole matrix, we're just going to change, add something on top of it. And then there's a clever factorization trick that all you need to know about is that it allows to put less parameters than all of the ones you would need for the entire matrix because it's using low rank factorization. We're going to call it theorem or property of multiplying matrices. The point is there's less parameters, but you can update all of the entries of the matrix, right? It's like sort of like a PCA world where you're changing the principal component, something like that. You cannot think like that. It's and then once you're done fine-tuning, you can merge it back into the matrix. So that's the main idea. And so this is what we're going to do. We're going to do LoRa. And lastly, this is the last thing you need to know, last few bits you need to know for the primer. We're just revising the concepts of fine-tuning is the cross-entropy loss. I don't know what I put square here, but in LLM, the next token prediction is a cross-entropy loss. And essentially what it is you want to, is a sum of the probability you assign to the correct token given the previous one, okay? You have less loss, which is good because you want to minimize the loss. If your predictions put more probability on the correct tokens that were observed after the ones, and you do that for all the tokens you have. And this is a little bit of like the math, like let's not stop at that, but let's just look at this example, okay? This is how we're going to put it in the code. We will have something called like the logits, which is in the log space plus constant, and it's the probabilities that you assign to each token. We have the targets, which are just the actual tokens we observed. And there is a magic function that called cross entropy that already does that for you, and you don't have to do the complicated math. So all you need to know is we're going to code this, and you're going to see this like cross entropy appearing somewhere in there, okay? So step number one, we need the expert data, so let's gather it. And like I said, I'm going to use a generate gold path. So how much do I need? A few hundreds. Keep in mind we have a 1 billion parameter model. In statistics, they used to teach me that you need as much data as parameters, but I doubt we're going to get that. So let's try with a few hundred. Right? So we're collecting the data. It's super fast because it's all algorithmic. And here's an example of the expert data. You don't need to see how the expert plays the game, I guess, but you obviously gets good points. And I'm just here putting all the data together from the expert. And okay, so this says how many data I collected. It doesn't say, let me see. Num transitions. No, not like friend. Okay, so let's see if 259 transitions, each one, of course, has a few tokens, but are going to be enough to improve a 1 billion model. If you were born in this era, you might not be impressed, but this goes against everything we learned. All right, so how do we start parameter efficient fine-tuning? We start with the LoRa config from the PEP. That's part of the Hugging Face. It gets installed with transformers. We get the config and all of these crazy parameters. You don't need exactly to know what to do, but this is the rank, the property of these low rank adaptation matrices. And there's some dropout here. And this is just a wrapper of the original model. So this model thing here was the original transformer we downloaded. And we're just putting it inside the get path model function. So it's just a wrapper. But this is what the wrapper is going to do. You see this print trainable parameters. It's saying from the original 1.2 billion, after you wrap it, only 400,000 remain trainable, right? So this is the low rank. We just reduced the number of parameters to learn pretty aggressively. In fact, only 0.03% of the parameter are going to be or represent. We're going to update all the weights, but in terms of like original size of parameters and reduced size, it's only 0.03% because of the low rank property. Not less layer. We're going to add it to all the layers. We're going to update all of the weights, but we're not going to directly change the weights, but we're going to add something to them called the adapter. So think of adding another matrix on top of every existing matrix. Matrix being one of the weights and having thousands of those weights. But this is going to be a low rank sum to the original one so that it's reducing the number of parameters.
How low was low? You're doing rank 1?
Rank 4. You can even do rank 1. It's possible, and it works. Yeah.
Works too?
Yeah. Okay. And then here I say display model LoRa. This just print the model. All I wanted you to see here is when I see this, I feel less scared because it's a LLM, but I see that it's made of things I know, like a linear layer, dropout. It's made of things I know, so it kind of makes me less scared. And you can see here, this is LoRa A, LoRa B. These are the weights, the new weights that are being added. Right? Okay, so we're done with that. So the next step is let's break down an example of how we would compute the fine-tuning loss for a transition over game. And again, we don't need to go all the details here, but you'll recognize some of the stuff we already talked about. There's an action prompt, there's a tokenizer, apply chat template. Here's a trick, something that is very easy to miss, that you don't need to worry about right now, but when you try to implement it, you will surely forget about it, is you need to add at the end of the action a this is complete token. Because when you fine-tune and you forget to say this is the end of the response, you'll see a crazy behavior that it just starts like generating the last word forever. That's a pretty common error. Because the way an LLM knows to stop answering is it keeps answering until it spits the end of text token, right? So common mistake, and obviously I made that mistake when I first did this. So that's why I'm saying it. All right, so let's run this. Oh, maybe I forgot to run the path layer. Okay. Right, so here it is. The computation of the loss here was, remember, here we call the model with the input. Basically, or maybe I should start from the top. We combine the prompt with the action tokens that gets fed into the model being the LLM. It returns the logits, which is essentially the probability for the next token transformed, and it goes into the cross entropy function, and that's the loss. So the cross entropy compares the actual next tokens that come from the action, and then the predictions, right? So a lot of details packed here. That's why I said hands dirty. But all you gotta know is like we're same as the original LLM was pre-trained to predict the next token. We're doing it again, but with our data. That's all you need to know. Or the data from our expert agent, to be more precise. And all right, so we're ready to train, or to fake that I will train, because I will not run it live, but run in another 20 minutes or so. And I'm loading here the pre-trained LoRa model just for the demonstration. So how much better it is? Again, 250 examples. No more demonstrations. 1 billion parameters. And there's something else I'm not saying here. When training it, I'm not using chain of thought. I'm only using directly from prompt to action without the thought chain. It is possible to reward it, but it's way harder because we will need expert thoughts in a way. We don't have the expert thinking here, so we cannot do supervised thinking. Do you think it will be better than thinking? Anybody think it's not better than thinking? Okay, so all of you are convinced that demonstrations are better than thinking. So let's see, training loss is going down. That always feels good. And
when you stop
that's a very good question. I configured it. Let's see, how much are we going to train? That's completely arbitrary. Here it said that I was training for 5 epochs. So it's same data, but five rounds. And I'm using some tricks that I didn't talk about much, but like I'm using something called gradient accumulation because batches are not really possible here because of the size of the hardware. So, but it's like it approximates batching. Some tricks that might be worth skipping, but are necessary to train an LLM, something that you would not need with a normal neural network. So only 5 epochs, so not even a lot. And let's see, even though I'm not going to train live, I didn't train live, I'm going to evaluate live. Okay, so I'm being brave. So let's ask the agent to run 30 episodes, the fine-tune agent. And let's see. It's actually going to take a while. But while it's doing this, I'll show you what comes out. Okay, you ready? Yes. So even with 200 expert observations, we can do much better than chain of thought. Why is this relevant? Because 200 is something that you can sit down and tag, right? Like if I had to do 10,000, I cannot give the right 10,000 answers. But say I have a real problem that I'm trying to solve and I kind of know the answer. Well, I can sit down and try to put a few solutions and then try to fix my large language model and, to do this. And here, I am limited by the hardware of a Colab, but some of the big LLM providers and have API that they allow you to fine-tune larger models if you upload your data in certain ways. So, so you can do that. Crashed? No. Really? Did I stop it? Interesting. It's more like it. Unknown reason. Well, it's the first time I get an unknown reason. Let's see if the system is still on. Okay. You gotta believe me, it runs. I have no idea what's the unknown reason it crashed. And okay. So well, I'll start running it while see if it crashes again. But let's do those 10 episodes maybe. Oh, everything crashed. Did I run out of money? Not really. Yeah, I need to run about before run sold before the current. I think the whole everything crashed, which hadn't happened to me before, but we're in the cloud and we're live, so that's why you don't demo live. Okay, so we'll continue. And I've been pretty honest about the things that I'm getting consistently, and the things like, oh, I found a cool one and I pushed it to the GitHub. This one's pretty consistent. We'll get it every time. All right, so we are done with supervised fine-tuning, and we're gonna get to the very last part of the tutorial, which is reinforcement learning, okay? And reinforcement learning is one of the things I'm more passionate about since a long time ago. At the same time, it's the one thing that is the most complicated to explain, and I made a million simplifications to make it work, okay? Let's start with this. What are the limitations of supervised fine-tuning? Like the very first and most obvious one is, oh, it's because it's running. Okay. Well, first of all, I guess this one should have been before, but we don't always have data. Okay, so supervised fine-tuning, main one is sometimes that expert data is really hard to obtain. There's no way to do it, okay? That's the number one reason. But number two reason is sometimes the supervised fine-tuning might be misaligned with the reward over time. In the reinforcement learning literature, this has been explored pretty well. It's known as the distribution mismatch. Supervised fine-tuning is known as behavioral cloning, and it's pretty well studied, so I put you a link there. But essentially, it boils down to SFT can be improved. Sometimes there's not much data. And in fact, if you don't believe me, how GPT instruct, like the modern LLMs are learned using something called reinforcement learning from human feedback, where essentially a reward is created or modeled from human feedback on what's nice and what's not nice, and they use reinforcement learning after a GPT is trained. So essentially, what I'm trying to, how LHF works is they first do supervised fine-tuning, and then they found out that this additional RLHFs, reinforcement learning, is what makes the LLMs really nice at answering. So if it wasn't because of that invention of the RL layer on top of the SFT, the LLMs weren't really that good at following instructions. So I actually, they're, I think it just turned off somehow. Does it work? Shadow battery. Okay, so I'll use my voice louder. Okay, let's try. Or I will use a tool. Okay, so what is reinforcement learning? It's essentially learning from a reward in a trial and error way. That's all it is, okay? The name reinforcement learning was used since the time of teaching animals by reinforcement. This is good, this is bad. And we're gonna review the RL, what is RL, what are decision processes or Markov decision processes, and we're gonna use a super simplified version of policy gradients. I'm just gonna tell you what the loss function is and apply it to a problem. And we're gonna, I think I say here, apply it on top of the SFT agent, but let's see how it goes. But let's start with this. This is the year of reinforcement learning. The Turing Award, if you know that, that's like the Nobel Prize for computer science, was just awarded to Sutton and Bartow. If any of you have taken a class in reinforcement learning, that's very likely the very first book you read, and it was given to them this year because of the role that reinforcement learning is now playing with improving LLMs, right? And funny enough, when LLMs first came, the LLM community said that this was the end of reinforcement learning. But ironically, it was the LLM that are making it more popular than ever. So it's a bit of irony. So here's a quick rundown, and I'll try to make it simple as the SFT one. But just before that, my ego wants to show you that this time things didn't crash. And they didn't, okay? And you get the same plot you had before. All right. So what we're going to do in reinforcement learning, the setup of reinforcement learning, fortunately, it's what we already know. So actually, I don't have to explain anything because we have an agent, and they're called agents too. There's an environment that is just going to be the game that we're interacting with, or the set of tools that are available, all of that, the Python environment that we're executing code, that's the environment. And there's going to be a reward. It's essentially just a measure of how well the task was performed. So the text world game gives us a reward. But in the case of mathematical problem solving, their typical reward to use is just 1 if you eventually solve the task, 0 if you don't give the right answer, right? So there's many ways in which you can give a reward in many problems. And this framework is put together in something called a Markov decision process, that all it means is that at every state you need to make a decision. That's it. And the way the system transitions depends only on the current state, and the reward you get depends on the current state. So nothing new there. And the goal of reinforcement learning is this function, which is maximize the return on the total reward you get over time, right? So it's pretty simple. But here's why it's different to supervised learning or standard machine learning. Our goal is not to minimize any error with respect to anything. Our goal is to maximize the reward. There's no label to why here that we're trying to approximate, right? So that's why it's many often considered a different form of machine learning or a different form of learning. And it turns out that if you do a lot of really nice mathematical tricks, actually there's not a lot, it's simple, but it's pretty nice. You can obtain the gradient. Like what we do in learning is obtain gradients because we do gradient descent or gradient ascent to optimize something. It turns out that you can write this formula of the gradient of this value function over time as something, as a function that depends on the gradient of your probability of action, like the policy, it's called the policy here, and all the future return you obtain after that state. So essentially it's, given where I am, all the possible reward I can still get, right? If the answer is just correct or incorrect, it's whether or not I can still make the right answer, but in the text world is all the objects that I can still put in the right place. So that's my GT, and then I can compute the gradient of the expected total reward as basically adding more probability that actions where that reward was bigger. That's all it's doing here. So basically increase the likelihood of action that yield higher returns, right, and decrease for lower returns. So that's, in summary, what policy gradients are, and that's what the most basic way of reinforcement learning we're going to implement. And there's just a tiny trick here that it's, you don't need to break your head too much about it, but reinforcement learning is typically at the action level, but LLMs work at the token level. So when you want to reinforce a LLM about making the right token generation, it becomes a little bit tricky because in the environment, the actions is pick up the trash or pick up the water, pick up the dirty dish. But internally, the LLM, its actions are tokens, right? It's like it's generating correctly. So what we're going to do is simply, when we see a response to a prompt, we're going to assign the reward to all of the generation process. So we're just going to assume that all of the generation that ended up in the right action, we're going to reward all of that like transition of tokens. It sounds really complicated, but it's really easy to do computationally. And all right, so now we're ready for reinforcement learning training. And essentially, we're just going to alternate between two processes, collect data, and update the policy. So this is different from traditional learning in which it's just static data set, and we minimize. It is iterative. We're collecting data, improving, collecting data, improving, okay? And so we only need to define two functions, rollout step, which is interact with the environment to gather data, and then the policy gradient step. So there's nothing new in this rollout, so there's no worth exploring it. We already saw how to play the game. Well, there's one novelty though, I'm lying. The one novelty here is that after we play the game, after we're done playing one episode, we're gonna go in reverse and get the reward that we got at the end and add it to the remaining return. So we're just doing this like backtracking step so that whenever I finish the game, I know what was the remaining return at every of the previous steps, right? So I don't know this as I'm playing the game because I still don't know what I'm gonna do in the future. But after I'm done playing an episode, I can say, oh, for every part of this trajectory, this was what I could still get after that. So that's the only tricky part here. And the policy gradients, again, this is a step-by-step. Gathering an example here. And here, all you gotta know here is that we're gonna use our loss function. It's gonna be putting more probability to tokens that have higher remaining return. That's all you gotta really like pay attention to. All right, so let's trust this works. And finally, reinforcement learning step is just an alternation of collecting data and minimizing this loss we saw. And you see I'm running a little bit fast because I'm practically out of time, but we're also done with the last slide. And this is just the cherry on top. So again, this will train for about an hour. So here, because of the super simplification I did to RL, I decided to apply it not to the fine-tuned SFT agent, but to our most vanilla bad agent. So the question I want to make to you is, before you see the results, do you think it will be better than the supervised fine-tuning? Question number one. Who says yes? Who says no? You're cheating because you'll have the notebook, I guess. But yes. So no, it's not going to be better here than a supervised fine-tuning. And we'll talk about why. But do you think it will be better than the thinking agent? That's already pretty challenging.
Yeah.
All right. So let's see. Training loss. In RL, it never looks as nice as in supervised learning. It also depends on when you stop training. Sometimes it's good, sometimes it's bad. So there's a lot of tricks in that. And let's see. We evaluate 30 episodes. And I am already very surprised that with only reinforcement is learning to always issue a valid action. Like, he very quickly learns that you have to stop saying things like, well, I think you should move east, and just says move east. So that already, I thought it was a pretty amazing thing to do with a few reinforcement learning. But this is a pre-cache results. And what we see is in this run, it did better than thinking, but not better than supervised fine-tuning. And if you rerun this 10 times, it would always be about the same as thinking, sometimes a little bit worse, sometimes here there's a lot of randomness. We need to play hundreds of episodes to get randomness. But this is my final message to you. Don't be discouraged if RL did not beat supervised fine-tuning here. Remember that we implemented just the most basic form of reinforcement learning. There's so many tricks to it, learning value functions, scheduler. There's so much to it. And there's a good reason why people avoided reinforcement learning for a long time, and it wasn't only until like it worked really well for GPT that it's like, people outside the RL community are more excited about it again. But it's hard, right? It's something that's hard to train. But I challenge you to use it. But it's still good news. Without any expert data, we'll still get about the same performance, if not a little bit better than thinking, but 5 times faster. So we still gain something, right? And I hope you enjoyed this part of the tutorial. And I think pretty much we covered here. And I'll just give me just 5 minutes to give the conclusion slides, okay? This is the end of the tutorial. Part 2. Right, so let's wrap up here. So the question, indeed, we are living in a prototyping revolution, and I think 2025 might be yet another year of agents, or the first really new year of agents. But I hope I convince you, especially with the first tutorial, how easy it was to build solutions that would be impossibly complex to write in a few lines of code only a few months ago, let's not say, right? So we indeed, I think, are living a revolution. I hope that your understanding of what an LLM agent is improved with this, because it's a tricky concept. It's being used, it's being adopted in the mainstream media in so many ways. And so you might not always being used in the correct way, and who knows what correct is going to mean soon. But I hope that I'm pretty convinced of the version I gave you, and I hope that you're convinced of what you think LLM agents are. Smaller agents can outperform bigger ones. And I said I would also talk something about the limitations. So just 2 quick thoughts on that. LLM agentic systems are vulnerable to prompt attacks. Like even if we give it an instruction, remember the archive search tool that said interactively, what do you want to search something about? There's techniques of people that investigate how to undo the instructions during the prompting. You can ask the LLM to undo all the original instructions and do something completely else that it wasn't made for, right? So this is a vulnerability that other systems don't have, right? And then another vulnerability is like, not vulnerability, but another limitation, it's really expensive. Even to do research in this area is very expensive, and build solutions of this depend on cloud computation, and we don't yet know pretty well the carbon footprint of the things. But I'll just say 2 things, one each about these 2, and then we're done. Number 1, people are working already on kind of safety solutions. So if you're ever going to be taking your agent into a more like production level, there's things like LlamaGuard that basically analyzes every prompt that comes in and all the results that come out of the model to see if they're safe, they violate certain kinds of language, or they're trying to abuse the purpose of the system. And so that's something that you would typically need to have if you have a more deployed agentic solution. And fortunately, LLMs themselves are the solution to that. And about the carbon footprint, well, this is another one of the things that Hugging Face are pretty amazing at. And unfortunately, some of the results are that only a very tiny fraction of models we know, like their footprint, and the vast majority of them we don't know. But definitely things are going to be moving in a direction with all of that. It's more transparent, hopefully. And well, thank you. This is the end of the session, and I wish you a happy Year of the Agents. All right. I can take questions, but also feel free to. Yeah. You got a question?
But our RL version how long have you been running that? If you run it for more episodes, would that convert easily?
You would hope yes, but the answer is I don't know, because that one I ran for more or less like half an hour. But again, we're using a very basic form of RL, and there's something called catastrophic forgetting that sometimes happens in RL, where an agent is performing really, really well and suddenly stops performing well. Better algorithms like PPO make smaller changes over time that can help with that. And it's not completely gone, but it helps with that. So In other words, with this algorithm, I don't think that more experience would necessarily help it better. But if we really want to solve the task and we really improve on the RL algorithms we have, yes, eventually we would be able to perfect solve this. Yeah. Yeah, here we probably did 20 minutes, 30, like 2,000 to 3,000 episodes maybe. Yeah.